Alright guys, this is the last lesson in Unit 6 on integration. And so as we continue to develop our integration methods, in 6.4, we all these antiderivative problems are bunched together, and we need to come up with a way to find their antiderivative more effectively. First, you need to take out one of the formula sheets that I had you print out under homework number 10. More specifically, take out the one that is titled a derivative summary. Okay, and to the back of the first page, that's the derivative summary. You have a summary of all the transcendental functions derivative that you need to memorize, such as the derivative of e to the x, the derivative of just a general exponential function, the derivative of a ln function, the derivative of a log function, all the trig functions derivative, all the inverse function derivative. Okay. So, and then those are good for now. So review these transcendental functions. Take about a minute to do that. Pause the video, take a minute to review these. And once you have reviewed that, take out the page that's titled integration summary. And here is all the summary of the general antiderivative. Okay, GA for general antiderivative. So if there's a constant, then the antiderivative of that constant is going to be kx plus c. If you have a power function, then you increase the exponent by 1, divided by that same value plus c. Here is the antiderivative of e raised to a power. When you have e raised to a power, you keep the integrand as the antiderivative, but you also multiply it by 1 over the derivative of whatever the power is. So if you look carefully, the derivative is k, and that's why we have 1 over k. Here is another function. When you have 1 over more specifically a linear function, such as kx plus b, that's a line, right? Then its antiderivative will be ln, just like how you have 1 over x. 1 over x is kind of like a special case, but this is the general case. So when it's 1 over a linear function or a line, then it will be ln of whatever is in the denominator, but you also multiply that with 1 over the derivative of the bottom. We can prove this using u substitution. That's why there's a star here that it says linear only. But if you memorize this, then you don't have to go back to a lot of u substitution. Now here's one of the ones that we have been working with, the antiderivative of 1 over x, and that's ln of x plus c, absolute value. Okay. Here is the antiderivative of sine function. Sine, and the sine has an input, ax plus b. So what's the trick to that? Well, the antiderivative of sine is cosine, and then leave everything alone. And also multiply it by 1 over the derivative of the inside, which is a. Now that's negative because the antiderivative of sine is negative cosine, and that's why there's a negative in the front. The antiderivative of cosine a to the x plus b, same thing. The antiderivative of cosine is sine, so sine, and then keep the inside the same. Multiply it by 1 over the derivative of the inside, which is a. Here is the antiderivative of secant of x times tangent of x. That equals to secant of x plus c. We can prove this. We can prove this using the u sub if we need to. The antiderivative of cosecant of x times cotangent of x is equal to negative cosecant of x. This is just the opposite from these derivative. Okay, so the derivative of secant is secant of x tangent of x. So the antiderivative of secant of x tangent of x is secant of x. Once again, this is just going the opposite direction. So memorize these. If you memorize its derivative, then its antiderivative comes for free. Okay. Here are the important ones to remember as well. The antiderivative of 1 over, this is the same as 1 over, see, 1 over x squared a squared, or they can swap this around, right? There's a lot of ways to write that. They can have x squared plus a squared or a squared plus x squared. It means the same thing. It equals to 1 over a, whatever a is, and then arctan or tan inverse, because that's what arctan is, x over a plus c. Okay, that's arctan. This is arcsine. Another way to say arcsine is to say sine inverse. I have been using a lot of sine inverse in the classroom. Here is one for cosine inverse. Cosine inverse is very similar to sine inverse, but the only thing that's different is that there is a negative instead of a positive. Okay. And then here's last but not least, when you find the antiderivative of an exponential function that's not base e, then it is itself times it by 1 over ln of whatever that base is, which in this case we use the example, so it's base e. So these are all the general antiderivative. You should memorize all of these. If you memorize the derivative of the trig functions, then you get the majority of these for free. And if you memorize the derivative of the inverse functions like these, then its antiderivative will be similar. Okay, it will be similar. Now, when do you use substitution? Well, you use U substitution when there isn't any general antiderivative, because U substitution is a change in variable, and that change in variable will help turn it into one of these general antiderivatives, which makes it easier for you to find the antiderivative. So how do you recognize, or when do you use the U sub? Well, one way to know when to use U sub is it will involve two functions, more specifically an inside function and an outside function. The outside function will be the derivative of the inside function. You try to look for that pattern. That's one way to know when to use U sub. And also use U sub when the inside function is raised to a power. Perhaps this power should be larger than 2. That's when you would use U sub. Or from time to time, when it's raised to the second or higher, then you use U sub. You also use U sub when your antiderivative involves a quotient of two functions, but the numerator is the derivative of the inside of the denominator. That's another signal to use U sub. Okay, so make sure you review all the general antiderivative. Review that on knowing when to use U sub. Very important that you memorize all of these. It's also very important that you memorize these as well. The AP exam will challenge you and will definitely test you on your knowledge of these derivative functions. Okay, so now our main point for today is to know when to use U sub and when not to use U sub. So when you're given a problem, first thing you want to do is you want to decide if the integrand has a general antiderivative. So you might wonder, well, what is an integrand? Well, an integrand is the function that you're trying to find the antiderivative for. So then this whole thing right here is what we call an integrand. Okay. Now, if it has a general antiderivative, then you find that general antiderivative and you add a c and you're done. If there's no general antiderivative, then maybe you have to do some algebraic manipulation, and that could involve like distributing the x, and then the antiderivative will be obvious. Now, when none of those are the cases, then you try U sub. Okay, And remember, U sub means that you need to kind of look and see the fact that it's a product of two functions.